Okay, so what is it that we are doing? We were doing this, so Lebesgue integration. So even let me go one page previous. So Lebesgue integration is constructed in 3 steps. First step for non-negative simple measurable functions. Then for non-negative measurable functions. For this one, it is obvious how you should define. If you have A1 indicator, A1 plus AN indicator, AN, you define it like this. Here, I said it only when AIs are this is when AIs are pairwise disjoint and they form a measurable partition of X. And A1, small a1 up to small an are distinct real numbers, positive real, non-negative real numbers. Then the integral was defined like this. Okay. And then for non-negative measurable functions, we just find all non-negative simple measurable functions which lie below that. And we want all those integrals of these to be smaller than the integral of f. So we just take the supremum of that. It's a bit like doing, like somebody remarked the other time, it's like outer measure except you are doing from below. It's more like inner measure if you want. And then we go to general functions. We can break it into a difference of two. Break it into two difference of two non-negative functions. There's a very specific way we do it as f plus minus f minus. And both of them are non-negative measurable functions. So we just define the integral as the difference of the integrals. And then our goal was to get to this statement. Actually, last time I changed these notations. I called this I1, I2, and I3. One of the things that we want to prove is that they all agree. That is, if f is both simple, non-negative simple measurable function, then I1 and I2 and I3, all of them give the same answer for that. And if something is non-negative measurable, I2 and I3 both give the same answer for that. Okay. So these are not different things. They are the same thing. And so we will use the notation integral f of x f d mu over the space capital X. Everything is happening in the space x f mu. Okay, so that's one of the things that we want to prove. But more importantly, that is basic. But we also want to prove that this space of integrable functions, which is those for which the f plus and f minus have finite integrals, forms a vector space, and the integral is linear. Okay, the integral is linear. Secondly, it is positive. If f is a non-negative function, then integral is non-negative with equality if and only if f is 0 almost surely. Okay, so this is again a quick summary of all the things that we wanted to do. And what I did last class was to get to here, we have to go through the properties of I1, I2, and I3. Each step we have to go through it carefully. And last time I went through I1 reasonably carefully. I think I have I have not completed what I wanted to say in I1. So let's come to this. So what we want to do is first understand I1. This is defined for simple non-negative measurable functions. So when it is in this form, this is we call the canonical forms. A1 capital AIs form a measurable partition of X and small AIs are distinct. That is the canonical form of a simple measurable function, simple function. Then we showed one convenient thing we showed was it doesn't matter even if you represent the simple function in a different form where these sets may overlap, the indicators may have overlapping sets and BIs are not distinct, etc. Even then, the same formula for the integration holds. So I1 of G, if G is like this, I1 of G is this, irrespective of whether BIs are disjoint or small BIs are distinct, etc. And we showed this. After showing this, it was easy to show that the integral is additive and it has the, so if alpha and beta are non-negative, we can't take linear combinations because we want to stay in non-negative functions. This is what is called a cone. Okay, cone is something where you can't multiply by negative numbers. You go to the other side. So anyway, so if alpha, beta are non-negative numbers, then this type of non-negative linear combination of f and g will be another non-negative simple measurable function and its integral will be that linear combination. And also we showed the monotonicity. If f and g are simple non-negative measurable and bound f is less than equal to g pointwise, then the integrals are also ordered. This we could show, and it was very convenient because when you add functions and so on, it is a bit of work to get it into the canonical form. But because we had this lemma beforehand, we could do that. We didn't have to come to the canonical form, and we proved this. Okay, that we proved. But here is the more important property that we need to prove. This is what is called a monotone convergence theorem for simple functions. This will be not, it's not clear why now, but it is required for the next step. When I go to I2, which is the integral for non-negative measurable functions, not just simple ones, then this will be required. Okay. So what is the monotone convergence theorem for simple functions? It says that suppose I have, it's everything is about simple functions only here. So I have phi 1, phi 2, phi n, all of them are non-negative simple measurable functions, okay? And also increasing, phi 1 less than equal to phi 2 less than equal to phi 3 and so on pointwise. And so that will obviously converge x by, for each x, phi 1 of x, phi 2 of x is an increasing sequence. So that will converge to some number which we call phi of x, okay? So phi n's are but we assume that this phi is also non-negative simple measurable function. Okay, so phi and phi are all simple measurable non-negative, and phi n's increase to phi pointwise. Then the I1 of phi n increases to I1 of phi. This is what we want to prove. Okay. Any questions so far? What I will do is now I will proceed. So up to here is recap. Now I have to proceed to prove this. Any questions here? Okay, if not, let's proceed. Okay, so by monotonicity, I have already proved monotonicity right here. F less than equal to G, both non-negative simple measurable, then I1F less than equal to I1G. So monotonicity implies so 0 less than equal to I1 of phi less than equal to I2 of phi, sorry, I1 of phi 1, I1 of phi 2 less than equal to I1 of phi 3 and so on. And all of them are also bounded by I1 of phi. I can apply the inequality with phi n and phi and see that they are all bounded by I1 of phi, because phi is also assumed to be simple and measurable. Okay, so this is true. So the limit exists. So what it implies is that limit I1 phi n exists and is less than equal to I1 of phi. So these are increasing numbers and they are bounded above by this. So the limit exists and is bounded by that. The point is to prove the other way. The harder part is proving that this is greater than equal to I1 of phi. Okay, so this is what we have to prove. How do we do this? So this is the key part. So you have to use that these are simple functions. The first one just use monotonicity. Now we actually use these are simple. So let's write phi in its canonical form. Okay, so let's write it as C1. Let's call it alpha 1 indicator A1 plus alpha n. Okay, so let me do one thing. So I just indexed it from 0 onwards, just that A naught up to AN is a measurable partition. Of X, and alpha 1 up to alpha n I assume are positive, strictly positive. So alpha naught is actually 0 is what I mean. But if your function doesn't take the value 0, you can ignore this term. So if there is the 0, if 0 is in the range of phi, then that part I put it as the 0th one. Okay, so that's all. If it's not there, ignore first somewhere. Ignore first sum. Okay. So then, so this alpha is a strictly positive. Alpha 1 up to alpha n are strictly positive. So what we do is phi n's. So AK is exactly where this is alpha k, right? So this means that this is a measurable partition. So maybe there is a part where it is 0, but this is where it is alpha 1. This is where this is alpha 2, and so on. Alpha n. So here is where it is 0. Maybe that's an empty part, but we don't care. Okay, so now we see define a. Let's define a n. So how many? Oh, sorry. This I should not have used n here. Maybe that will confuse me, I'm sure. So let me just change this to some other number, maybe m. So n I am going to use as index of the sequence. That's all. So let's take a n k to be the set where phi n is bigger than or equal to alpha k into 1 minus epsilon. Let's take intersected with ak. Okay. So ank is where phi n is nearly taking the value alpha k. Okay, see phi n's increase to phi. So ultimately close to the values of phi n on this set will be close to alpha 1. Values of phi n on this set will be close to alpha 2 and so on. But there is no uniformity of convergence. We have to be careful. Therefore, we define this set ank is the subset of ak. So an1 is the subset of this part where phi n is more than alpha 1 into 1 minus times 1 minus epsilon. Since I assume they are strictly positive, I can write minus epsilon into 1 minus epsilon. It doesn't matter. So let's write it like this. And then what we see is that phi n increases to phi, right? Implies that this sets a and k increase to ak. For k equals 1 to up to m. So this I do it only for 1 less than equal to k less than equal to m. So I know the part where it is 0, I don't care. I don't define that. Only on the remaining parts I do this. So is this clear? Because phi n, if phi n is bigger than this, phi n plus 1 is also bigger than this. So a n plus 1 k will be anyway larger than this, meaning the set will be larger. Okay, so if phi n is larger than this one, then phi n plus 1 will also be larger. And also at each x, phi n of x converges to phi of x. So this phi n of x converges to alpha 1. So any x here ultimately will lie within this, because phi n of x will have to get close to alpha 1. And here phi n of x will have to get close to alpha 2 and so on. So this is clear. So now you consider, so now so then let's define a new simple function psi n, which is alpha 1 into 1 minus epsilon into indicator a n1 plus so on up to 1 minus epsilon alpha m indicator a n m. Okay, so we just on these sets we define the values to be 1 minus epsilon alpha 1, 1 minus epsilon alpha 2. I mean on a and k I take the value, psi n takes the value 1 minus epsilon alpha k. That's all. So then what is the point? Phi n is greater than equal to psi n. This is also a simple. This is also simple, non-negative, and measurable. Simple, non-negative, measurable, and phi n beats psi n because psi n is 0 outside of these sets. By the way, outside of an1, an2, anm, these are anyway pairwise disjoint because an1 is some subset of this, an2 is some subset of this, and anm is a subset of this. They are pairwise disjoint. And phi n beats psi n on each of these sets. Outside that, this psi n is 0. So phi n greater than equal to psi n pointwise. And of course, phi n is yeah. So hence integral phi n d mu. Oh, sorry, no, I use the, sorry, I don't use that. I use I1, right? I use the symbol I1 provisionally. So I1 of phi n is greater than equal to I1 of psi n, which is 1 minus epsilon alpha 1 mu of a n1 plus alpha m mu of a n m. Note that the number of terms is not changing. Okay, so that is the point of moving from phi n to psi m. Phi n is a simple function, but how many parts it has, we don't know. It may be having increasingly large number of values. So we would like to fix the number of terms. That is the convenience of this. Psi n has only m different values. And this is the integral. Okay, so the 1 minus epsilon multiplies everything. Sorry. 1 minus epsilon multiplies everything. And this actually increases to 1 minus epsilon since an1 increases to a1. So that increases to alpha 1 mu of a1 and so on. And this increases to alpha m mu of am. Which is nothing but 1 minus epsilon I1 of phi, right? Because what is I1 of phi? Alpha naught is 0, by the way. Alpha naught is 0. So I1 of phi is exactly this thing inside the brackets, alpha 1 mu a1 plus alpha m mu m. And the convergence here is because an1 increases to a1, the measures increase. So this is what we get, and this is true for all epsilon. So, so this as n goes to infinity. Hence, limit I1 of phi n greater than equal to 1 minus epsilon I1 of phi for all epsilon positive. So that finishes the proof. So it's true for all epsilon, hence it's true. I mean, so that limit is greater. So this is the monotone convergence theorem. Any questions, or if there is something not clear, I can repeat. Okay, so this will be very useful in the next part, the second part. So what we have to do is we go to step 2 and prove something very similar to this. Okay, very similar to this proposition. Okay, we want to prove exactly similar thing for step 2. Okay, so maybe I will go to the next page rather than I can keep erasing and writing there, but maybe it will be confusing. So we go to step 2. So we now look at I2. So for f non-negative measurable, remember that I2 of f is defined as supremum of I1 of phi, where phi is sandwiched between 0 and f, and it is simple and measurable. This is how it is defined. Okay. So what are the properties we want to prove here? So the statement is, so the proposition we want to do is that if fg non-negative measurable and alpha beta are non-negative real numbers, then alpha f plus beta g is also non-negative measurable, and its integral, that is I2 of h, is going to be alpha I2 of f plus beta I2 of g. Okay, that is step 1. Maybe I call it 1. 2. Same. If f is greater than equal to 0, implies I2 of f is greater than equal to 0 with equality if and only if sorry, I want to write it in the other way, the monotonicity, f greater than equal to g, then I2 of f greater than equal to I2 of g, with equality if and only if f equal to g almost surely with respect to mu. That is the set where f is not equal to g is 0. That has 0 measure. Okay, so here f and g both non-negative measurable. Okay, both non-negative measurable. Another thing that I want to prove, let me write down I2 if f is simple non-negative measurable, then I2 of f is same as I1 of f. I2 of f is same as I1. Okay, so these are the things I want to prove. And then we will be able to proceed to step 3. Okay, so the proof is again, it's a little bit of actually the main part is done. Main part of the monotone convergence theorem for simple functions. That's the key part. After which it is actually straightforward. Now this is a simple matter of bookkeeping. Yeah, how do you prove it? So first one. That's the non-trivial. This is the non-trivial part actually. This one is the most non-trivial, and monotone convergence theorem for simple functions will come in handy here. How is that? Okay, so one is okay. Let's look at this. So let's firstly let's separate this into two. Okay, I don't want to write all this. So if f is non-negative measurable, so is alpha f, and alpha greater than equal to 0 is a real number. Then alpha f is non-negative measurable. Also, phi is between 0 and f, if and only if alpha phi is between 0 and alpha f. What I'm trying to do is I'll separate the linearity into two parts. One is scalar multiplication, one is addition, just for convenience. That's all. Okay, so this way we can separate it into. So this is scalar multiplication. So from here, so the supremum here, where I define I2 of f, supremum is over all such phi. When I define I2 of alpha f, the supremum is over all simple functions sandwiched between the two. But any simple function sandwiched between 0 and f, you scale by alpha, you go there. It will be sandwiched between here. And any simple function here, you can go back down by dividing by alpha. So if you call this psi, then this is psi over alpha. So this way, it is very clear. So from here, it is clear that I2 of f, I2 of alpha f will be sup of I1 of alpha phi. So it is actually supremum. Okay. Yeah, so I think I can write this directly. Supremum of I1 of alpha phi, where phi is sandwiched between 0 and f. Instead of taking simple functions sandwiched between 0 and alpha f, I am writing them as alpha phi, where phi is sandwiched between 0 and f. And I already know that I1 has the homogeneity property. So that brings out alpha out of this and then out of this. So I will write as supremum I1 of phi 0 less than equal to phi less than equal to f, which is same as alpha I2 of f. So that way under scalar multiplication is okay. So what is interesting is the question of f plus g. So suppose fg non-negative measurable, then h is f plus g. Let's take. So it is non-negative measurable, that is clear. There is nothing to prove there. It's non-negative measurable is okay. Now if one way is clear, so can we do it like this? Can I, so here to calculate I2h, I have to take simple function sandwiched between 0 and h. For I2 of f, I do the same way for simple function sandwich. So if let's say 0 less than equal to phi less than equal to f, 0 less than equal to psi less than equal to g. phi and psi non-negative. So phi psi, let's just write simple measurable. So this certainly implies that phi plus psi is sandwiched between 0 and h, right? But the other way is not clear. I mean, other way is not clear. So if I take one simple function sandwiched between 0 and h, can I break it into two simple functions, one sandwiched between 0 and f and one between 0 and g? That is not clear. So this is a one-way inequality from which what will we get? So what will we get from here? So here what I can do, I will just say in words, I can choose phi such that I1 of phi is close to, okay, so let me write it straight away here. Let this be the case such that I1 of phi is greater than equal to I2 of f minus epsilon, and I1 of psi is greater than equal to I2 of g minus epsilon, right? So you can, it's 4 o'clock. You can find simple functions such that they come close to the supremum. So what this will imply is that I2 of h, since this is also, this is simple and measurable. So this implies that I2, this is in the supremum set for I2h. Therefore, I2h is greater than equal to I1 of phi plus psi. But since we know the additivity of that, that is I1 of phi plus I1 of psi, and that is we know greater than equal to I2 of f plus I2 of g minus 2 epsilon. Okay, so this is true for all epsilon positive. So implies I2 of h is greater than equal to I2 of f plus I2 of g. Okay, so this is what we get. Can we go the other way? That is not clear because this is contained here. To go the other way, what you would have to do if you try this way is to take a simple function sandwich between 0 and h and break it into two parts, one sandwich between 0 and f and one sandwich between 0 and g. That is not clear. That is not clear, and we will not do it like that. Instead, what we will do is, here is where it helps. So to say the other way, to prove this, so pick. So what is I2 of h? It is supremum over simple functions bounded by h, right? So pick any phi between. Okay, so that may confuse between this phi. So let me call it, give it a different symbol. Let's call it theta. So pick a theta, which is a simple function, which is it between 0 and h. So this is simple and measurable. And so what I want to, so since I2 of h is supremum of this, what I will show is I2f plus I2g beats I1 of theta. If that is true for all theta, then it beats I2 of h. Okay, so that's what I want to do. So let's fix this theta. And what do I do? Yeah, how do I do it? One second. Yeah, how do I do this? Okay. Suppose there exists phi n and psi n. So, okay. Sorry, let me make it cleaner. Phi n. These are going to be simple non-negative measurable, which increase to f. So phi n's are going to be again simple non-negative measurable, and psi n that increases to g. this also will be the same. So what I want to do is I want to find sequence of simple functions which increase to f, sequence of simple functions which increase to g. They have to be non-negative and measurable also. Suppose I manage to do that. How? That is a question. We have to show that is possible. But for a moment, let's suppose that is possible. Then what you do is you look at phi n min theta. Sorry, no, that doesn't make sense. What did I want to do? I want something. No, sorry. Then phi n plus psi n. Phi n plus psi n increase to h. That is clear because phi n increases to f, psi n increases to g. So they increase to f plus g, which is h. Hence, if I take phi n plus psi, phi n plus psi n, and I take min with theta. Okay, see, these are, so I want to apply monotone convergence theorem for simple functions. So I want the limit to be also simple, which is not the case in any of these three cases. F, G, and H need not be simple. So I take min with theta. Okay, so these are again non-negative, simple, measurable, and they increase to, what do they increase to? They increase to theta because these alone, these increase to H, right? And H beats theta. Right, so what will this increase to? This should increase to h min theta, which is same as theta, because theta is less than equal to h. So that's why this increases to h min theta, and that is same as theta. So these things increase to theta. So we can now apply monotone convergence theorem. The MCT for simple functions gives I1 of phi n plus psi n increases to I1 of theta. Okay, but what is this? This is I1 of phi n plus I1 of psi n. But of course, that is less than or equal to I2 of f plus I2 of g. Okay, so because phi n's are below f and psi n's are below g, right? So this is true. So what we have found is that I2f plus I2g is greater than equal to what? So in the end, so what this implies is that I2 of f plus I2 of g is greater than equal to I1 of theta. This is
So
yes.
I1
Yes.
of phi n plus psi n does not increase to I1 of theta. I1 of phi n plus psi n min theta increases to I1 of theta.
Sorry. Yes. Okay. I made a mistake. So that is okay. Sorry. Yeah, you are right. So let me just erase and write again because okay. Thanks. Yeah, that was a mistake, but the inequality goes in the right direction. Yes. So what we have is, sorry, this function is what increases to theta. So what we can say is that I1 of phi n plus psi n min theta increases to I1 of theta. So that's what monotone convergence theorem says. But by monotonicity, this is at most I1 of phi n plus psi n. That only makes it larger because this is minimum with theta. So this function is below this. And then this is I1 of phi n plus I1 of psi n. And that is bounded by I2 of f plus I2 of g. So overall, I get the same conclusion that I was writing, that I2f plus I2g is greater than equal to I1 of theta, and this is true for all theta which is between h and 0 and simple, measurable. So you take sup over theta, you to get I2 of f plus I2 of g greater than or equal to I2 of h. Okay, so that completes the proof of the first part. Okay, that's the proof of the additivity and this one. Okay, so this is really the hardest part. The rest of it is trivial. Okay, so the only part that requires this is this. Indeed, this is the key part. This is actually similar to, I mean, many things here are similar to the troubles we had in measures, except that we already have solved the problem in measures. So it's not actually, we are not going back to basics. In some sense, we are using the facts about measures. So it's like in outer measure was subadditive, but not generally additive, right? And then there was trouble when we had to show that on certain class of sets, outer measure is actually countably additive. That's not so easy. So it is a similar issue here that this additivity, I mean, one way super additivity was clear, but the other way is not clear. And but we are already using the properties of measures in proving the monotone convergence theorem. Therefore, it's not as difficult or anything like that. We are using things that we have done. So anyway, this completes the first part. So we have proved this. So we have proved this one now, because both scalar multiplication was easy, addition was the thing. Then the rest of it is very trivial actually. What is the proof of 2? I mean, 2, there is nothing to do. 2 is obvious. What is it saying? Okay, oh, okay, one thing is obvious. See okay, so let's not say obvious. So it is, so one part is obvious. If 0 less than equal to phi less than equal to f, and this is simple measurable, implies 0 less than equal to phi less than equal to g, right? Hence, so what this implies is that hence I2 of g is greater than equal to I2 of f, because the supremum for the g, I2 of g is over a larger class of functions. But why is that? What the other part, which is actually very useful, I want to do, the equality holds if and only if f equal to g almost surely. Why is that? Okay, let's see why that is the case. Why equality holds if and only if this happens. Suppose, let's do it the other way. Suppose the set g minus f bigger than equal to delta. Okay, suppose that has positive measure. Suppose for some delta positive, that set has positive measure. Okay, so then so let's call this set, let A delta be this set, g minus f greater than equal to delta. Okay, so then g is greater than equal to f plus delta times indicator A delta, right? Do you see that? See if x, so what is this? So this is all pointwise. So we have to apply at g of x. So what is this is saying is g of x greater than equal to f of x plus delta times indicator A delta of x. Now, first of all, if x does not belong to A delta, then this part is 0 and gx greater than equal to fx, that's given to us. But if x does belong to A delta, then gx greater than equal to fx plus delta. And that's exactly what this is saying. A delta is chosen to be precisely that set where gx beats fx by delta. So this is true. Therefore, what this implies is that hence, so let me just erase this. Hence, I can improve here. Okay, if 0 less than equal to phi less than equal to f, then 0 less than equal to phi plus delta times indicator A delta less than equal to g. So this is simple. Everything is measurable. Maybe I stop saying measurable. So this is also going to be simple because I'm adding a linear multiple of an indicator function. So this this thing is also simple. So what this implies is that I2 of G is greater than equal to I1 of phi plus delta times mu of A delta. And true for all phi, which is sandwiched between 0 and f. So take supremum over phi to see that I2 of G is greater than equal to I2 of f plus delta times mu of A delta, which means that it is strictly bigger than I2 of f. Okay. So that is what? If f is so, but we are given I2 of G is equal to I2 of f. So this is a contradiction, but so thus, if you have the integrals to be equal, I2 of G has to be equal to I2 of f, then mu of A delta is 0 for all positive delta. So mu of, let us say, union A 1 over k. I want to take a countable union, that also is 0. It's a countable union of 0 measure sets. But that is precisely what is this set. This set is exactly the same as G minus F strictly positive. Because if Gx minus Fx is positive, then it's bigger than 1 by k for some k. So any x which belongs here and vice versa. So this is same as this. So this is saying that mu of G minus F positive is 0. That is G equal to F almost surely with respect to mu. Okay, so I just got out in detail how you show the equality part. The other part is actually simple. Any questions? Okay, so the third part is actually trivial. If f is simple, then this already the other day Shekhar had mentioned this. So we have proved monotonicity and so on. So it is very clear. So if f is itself simple, then yeah, what can we say? I mean, it is I2 of f is greater than equal to I1 of f, because f belongs to the set over which we take supremum. See, we take supremum over simple functions between 0 and f itself is simple, so that is there. But if 0 less than equal to phi less than equal to f, then we already know that I1 of phi is less than equal to I1 of f. So take supremum to get. Take supremum. On the left side, we get I2 of f, which is less than equal to. The right side is not changing, I1f. So that completes the proof. Okay, so that's all. Once you have monotonicity, this part is easy. So I2 and I1 agree on non-negative simple measurable functions. And we have the additivity and linear scalar multiplication by positive scalar multiples and monotonicity for I2. Okay, any questions? So that completes the second part. So it's only remains to go to the third part, which probably I can squeeze in here. Can I? Yeah, let's try. So now you come to step 3. You are working with general measurable functions. And what is it that we want to prove? I3. So what is it we want to prove? We want to finally get to this theorem. We are trying to get to this theorem. That one is that I3 agrees with I2 and I1 on, I3 agrees with I2 on non-negative measurable functions. That's one thing. and then this additivity and the monotonicity. See, the second part is actually okay. So let's just write it out again. Then maybe. So let's write out. So just let me recap the definition. What is the definition? If f is, oops. If f is measurable and I2 of f plus and I2 of f minus are finite, we say that f is integrable and set I3 of f equal to I2 of f plus minus I2 of f minus. Okay. So for the moment, let me just ignore that other thing where one of f plus and f minus can have infinite integral. Yes, that is convenient. But for the moment, let me ignore that. That's not, I mean, you can work it out yourself. I will not bother about that. So let me just concentrate on the main case where both, that's when we say that f is integrable. Okay, one thing to notice here is that this condition. So it is same as, so a point to note, mod f is f plus plus f minus. Hence, all three are non-negative measurable, right? I2 of mod f is I2 of f plus plus I2 of f minus by the previous step. Here we have shown additivity for non-negative measurable function. So mod f is f plus plus f minus. So this we know. Therefore, the finiteness of these two. Hence, f is integrable if and only if I2 of mod f is finite. Okay, so instead of saying f plus and f minus should have finite integrals, we can also say mod f should have finite integral in the previous step. Okay, so this is why actually this whole thing is actually, I mean, now we are using I1, I2, I3, later I will use integral notation. What we deal with here are absolutely integrable functions. So, okay, so there are no, if you remember your sums and series and or integrals, we don't at all study conditionally convergent integrals here. We only study absolutely convergent integrals, so to speak. These are functions whose absolute value also has finite integral. Only those things really behave well. If you take conditional sums, you know all sorts of crazy things happen, so we don't like them. So this is one point to note. So this is about, so that's absolute integrability. Anyway, so let's come back to this. So what is it that we want to prove? So let me write down some of the steps. Yeah, one point is that if f is greater than equal to 0 and measurable, then I2 of f is equal to I3 of f. Okay, so why is that? It's very simple, because f plus is f, f minus is 0. That's all. There is nothing more to prove. If f is non-negative measurable, then f plus is f, f minus is 0. Okay, so what are f plus and f minus? F plus is f max 0. F minus is, we take f min 0 and negate it. Okay, so if f is non-negative, then f plus is f and f minus is 0. So I2 of f plus is going to be I2 of f. And I2 of f minus is 0. So I3 of f will be the difference between the two, which is I2 of f. So that part is completely trivial. And what are the other parts I want to prove? I'm going back to this theorem here. So let's take second part. There is nothing in the second part, you see. If f is greater than equal to 0, then integral f greater than equal to 0 with equality. Instead of integral, I now write I3, that's all. Okay, for the provisionally I write I3. Equality if and only if f equals 0 almost surely. That's exactly the same as what I had already stated. If f is greater than equal to 0 and measurable, then I3f is greater than equal to 0 with equality if and only if f equal to 0 almost surely with respect to the measure mu. See, this is nothing but a restatement of this. Okay, or rather even use g is 0 and f is some non-negative measurable function. Then I2, we have put it for I2, but now we know I2 and I3 agree on non-negative measurable function. So this is the same thing for I3, that's all. Okay, I3 and I2 agree now. So I3 of f greater than equal to I3 of 0, which is 0, and that's it. So that's also trivial. So what remains then? Let me go back to that theorem. So this part, so the first part that if I3 extends I2 blah blah blah, that is done. Second part is trivial, that's positivity. And in the first part again, scalar multiplication and I have two things, scalar multiplication and addition. Okay, so let's do scalar multiplication. So if alpha is real and f is a measurable function, then I want to show that I3 of alpha f is alpha I3 of f. Okay, I should have inserted a sentence here, which I will now skip since I already wrote. I should have said if f is integrable, then alpha f is also integrable and I3 of f is blah blah blah. Okay, yeah, so maybe I insert here. If f integrable, so is alpha f, and this holds. I3 of alpha f is alpha times I3 of f. Why is this true? This is easy actually. What is alpha f positive part? See, to calculate I3 of alpha f, I have to look at the positive and negative parts of alpha f. Are they related to the positive and negative parts of f, which is what determine I3 of f. Okay, so what is the positive part of alpha f? Yeah, what is the positive part of alpha f?
Alpha times the positive part of f.
Is that 2?
Alpha should be positive.
Yeah, so it is alpha times positive part of f if alpha is greater than equal to 0. But if alpha is less than equal to 0, then it's not. Okay, so let's write separately. So let's just write the case. If alpha greater, so first let's take the case alpha greater than equal to 0. Alpha f positive is alpha f and alpha f negative is alpha f minus. So hence, you'll get I2 of alpha f plus minus I2 of alpha f minus. I'm writing it out because it should be clear why I had to do all this stuff here. Okay, I had to prove all this scalar multiplication property for I2, otherwise I would have trouble here. So now I can conclude that this is alpha times I2 of f plus minus alpha times I2 of f minus, which is pulling out an alpha, you get I3 of f. Okay, so what happens if alpha is negative? Then what is alpha f positive part? Yeah, it is negative of alpha f minus. So just think of the case when alpha is minus 1. What is minus f positive part? It is negative of, yeah, it is f minus, right? Minus f positive part is f minus. So it is same as minus of minus 1 into f minus. And alpha f negative part will be minus alpha into f plus. Hence, I3 of alpha f will be I2 of minus alpha f minus I2 of minus alpha f plus. Which is, the signs gets flipped. This is minus alpha is a positive number. Okay, so when applying the scalar multiplication for I2, be careful to not apply it with negative scalars. But minus alpha is a positive scalar. Therefore, you can write it as minus alpha times I2 of f minus. And here again minus alpha comes out and becomes plus alpha times I2 of f plus, which is again alpha times I3 of f. So in both cases it is easy. So scalar multiplication part is also easy. The thing to do is the addition. Any questions here? Is okay? Okay. So the last part that remains is if fg integrable implies f plus g integrable and I3 of f plus g is I3f plus I3g. Okay. Why is f plus g integrable? Yeah, this may be somewhat boring to listen, so I am not surprised if many have tuned out. I mean, these are steps you have to go through, but it's a bit boring to listen. I'm sorry about that. We'll get to something more exciting at some point. So f plus g is integrable. It comes from this observation. It's easy. Mod f plus g is bounded by, I mean, so this one. So for this, what we can do is mod, all I have to do is mod f plus g less than equal to mod f plus mod g. Hence, I2 of mod f plus g is less than equal to I2 of mod f plus I2 of mod g. I have used the properties of I2 here. I2 of this is less by monotonicity is bounded by I2 of this, which is the sum of I2 of mod f and I2 of g, which is finite. Okay. So see, this would be a bit of trouble if you had to do positive and negative parts, because what is the positive part of f plus g? Can you write it in terms of positive part of f and positive part of g and positive and negative parts of f and g? It's not so easy. Say if both f and g are positive, then it's fine. But if f is positive and g is negative, then the positive part depends on whether which is larger in magnitude and all that, right? So just give me a moment, just 1 second. So that is actually a small but tricky point actually. If you have to go through positive and negative parts, you can't write f plus g positive part in a easy way. Okay, so you will get stuck somewhat. Actually, the same will happen here. So now, how do you prove I3 of f plus g is I3f plus I3g? Okay, so this part is okay, right? I mean, so I have shown this. So how do we prove this? So let's see that. How do you prove this? For this, see, I3f is defined as I2 of f plus minus I2 of f minus. This is defined as I2 of g plus minus I2 of g minus. And this is defined as I2 of f plus g positive part minus I2 of f minus g, f plus g negative part. How am I going to handle this? It looks a little, because f plus g positive part, I don't know how to express in terms of these, right? So let's call this function h. Okay. Yeah, so what do I do? Yeah, how do I do? 1 second, I myself to work. Yeah, h is f plus g. Actually, it is a bit tricky. I always forget this one. So H is F plus G. Now let's write it in terms of positive and negative parts. H plus minus H minus is F plus minus F minus plus G plus minus G minus. Okay, see, I don't know what is H plus in terms of F plus and in terms of those. I don't know how to write H minus. But H plus minus H minus is H. That can be written in terms of this because it's just F plus G. Now what I do is I transfer everything so that I have only positive sides. H plus plus F minus plus G minus is equal to H minus plus F plus G plus. You agree? I just transfer so that everything has positive sign. So let us call it some function. Some function, I don't know what name to give. H, G, F, what are the names? V, okay, say. Just I have given a name. V is both this and this, just for convenience. What happens is, now I2 of V, these are all non-negative. Actually, I don't need that symbol. Okay, so these are all non-negative measurable. Everything here is non-negative measurable. Now I apply I2. I2 of H plus F minus plus G minus equal to I2 of H minus plus F plus G plus. Because everything is non-negative, the sum is non-negative measurable. But all these individual pieces are also non-negative measurable. Therefore, I already know that this is I2 of H plus I2 of F minus plus I2 of G minus, right? On the other hand, this is equal to I2 of H minus plus I2 of F plus I2 of G plus. Okay, so this sum is equal to this sum. Now again rearrange. So I transfer this H minus to this side. So I get I2 of H plus minus I2 of H minus equal to, I transfer these F minus G minus to the other side. I2 of F plus minus I2 of F minus plus I2 of G plus minus I2 of G minus, which is what you want to prove, right? That is same as I3 of H equal to I3 of F plus I3 of G. It's a bit tricky. If I leave it to you, I think you will get stuck. It's not. It's a little. If you try to express H plus separately in terms of F and G, and H minus separately, yeah. So you get into some trouble. Okay. So this is the clean way in which you don't actually do any work. It looks like cheating. It's not. So it works. So that's all. That completes the proof. So we have completed actually the construction of Lebesgue integral. Okay. So if you are sleeping, you can wake up, or you don't need that. There is nothing super exciting right now. But what we did was to prove this theorem that integrable functions. So we have now understood what integration is, and we have understood that it is a linear and positive thing. And yeah, so it's linear and positive. That's the main thing. And as I said, later you will see that anything that is linear and positive on a large class of functions is actually integral. Yeah, that is one of the theorems. So henceforth we will just write. So one point is, so henceforth we will write integral f d mu, or to be most explicit, f of t d mu of t, something like that, with a dummy variable. T doesn't mean anything. You can put anything there. Or sometimes we may just write f d mu if the space is clear, etc. in place of I1, I2, I3. Okay, so this is what we shall do. And this is called the Lebesgue integral. Okay, this is the Lebesgue integral. Yeah, what is it that I want to say? Let's see. Yeah, there are a few remarks I want to say, and afterwards go on to things like some limit theorems, monotone convergence theorem and all that. But before that, I want to nail a few remarks so to fix these things. Okay, so a few other basic properties. Yeah, I'm already here. Okay, so a few more observations let's make. Or maybe I go to a new page. Yeah, I'm not sure, not being very organized now. I'll see what I want to say. So here I want to put it's more like some remarks. Okay, so yeah, what are some things that we want to know about this? Right. Yeah, so let me just see. Yeah, one of the things. Okay, one of the things. It's an interesting point. Okay, at least let me do something that is interesting, so you can slightly wake up for a short while. So what is so what is really happening with all this Lebesgue integral? Okay, what is the big deal? How did something new happen? I mean, it looks like we did only boring stuff. So how did something come out? How does it compare to Riemann integral? Okay, so let us take. So let's consider the space. To understand that, we have to take a place where Riemann integral is well defined. So rather than go for all this improper Riemann and all that, let's work with on 0, 1. Let's work on 0, 1. Okay. So suppose, so when is a function? So when is a function? So when is a function Riemann integrable? So f from 0, 1 to r. Okay. So when, so how does a function fail to be integrable? That is the question that we should ask. Okay. So actually there are two reasons why a function fails to be integrable. So for example, what functions are Riemann integrable? Do you know? What functions are Riemann integrable? Do you know that? Anyone?
Discontinuities measure 0.
Ah, okay. So you have seen that. So there is a theorem of Vitali. Is that all? See, there is a trivial reason why a function need not be integrable. So there are two reasons why a function need not be integrable. One is a trivial reason, one is a non-trivial reason. What is the trivial reason? Just that it is too big. Okay. So the integration is some area under the graph, right? If that area is like very large, then you get infinity. So you say it is not integrable, right? So that is one reason why a function is not integrable. So to omit that, let's assume that be a bounded function. Okay. So bounded function. Then what you said is true. Okay. So f is Riemann integrable. So with this setting, f is Riemann integrable if and only if the set of x where f is discontinuous. at x, the measure of that is 0. The Lebesgue measure of that is 0. You see that in basic real analysis class, or you should probably. You may worry that, okay, you did not introduce Lebesgue measure, how would you have seen that? If you haven't seen, you will worry, but 0 Lebesgue measure is easy to define. A set has 0 Lebesgue measure if you can cover it with countably many intervals whose sum of lengths is arbitrarily small. So you can define 0 Lebesgue measure sets without defining Lebesgue measure itself. So that's what happens there. But now we know Lebesgue measure, so let's use that symbol. F is Riemann integrable if and only if the set of discontinuity points has 0 Lebesgue measure. Okay. So this is a theorem of Vitali. It's called Vitali-Lebesgue theorem or something like that. So this is okay. Lebesgue, we have given enough things are named after him. Let's just call it Vitali. Vitali also a famous guy, but not as much as Lebesgue. Okay. So what about F is Lebesgue integrable? In this setting, here with respect to, so here what is the measure space? We are working with 0, 1, the Lebesgue sigma algebra and lambda. Okay. So that's the, so what is Lebesgue integrable? When is it Lebesgue integrable? It's already a bounded function. So when will it be Lebesgue integrable? So you can go back to this and see I3 and so on. So here I3 was introduced, right? So where is that? Yeah, I forgot where it is. Step 1. Okay, here. Where on earth is it? Here, step 3. Okay. So function is integrable if f plus or f minus are both having finite integrals, right? And but that same as mod f has finite integral. So what is the condition here then? If f is bounded, is it integrable? Or is there any condition? Yeah, from what we saw, if it's bounded function on 0, 1, is it necessarily integrable or do you need a condition?
I think you don't need any condition.
You don't need any condition. You think it will be integrable. There is an implicit condition which you,
measurability is required.
It has to be measurable.
Okay.
Because we were only defining it for integration for measurable functions, right? So measurable function. Now the thing is, any function, so this is an exercise I will leave to you. There's no reason why we should spend time in class doing it, but it is a good exercise you can do. If you don't want to do, is fine. It's optional exercise. So it's a good exercise to try that if a function has countably, if a function has a discontinuity set of measure 0, then it is measurable. Okay, for this it's important you take the Lebesgue sigma algebra, not the Borel sigma algebra, but that's fine. So you do that and then you see that. So therefore, what this shows is that many more functions, Lebesgue integration is more general. In Lebesgue sense. In fact, the integrals will match. That part is also true. I am not going into that. Whenever Riemann integrable, then the integral will be same as Lebesgue integral. That is also true. You can why that is true. It's easy to figure out because Riemann integral is defined in terms of step functions, right? And then you can use monotone convergence, etc. For step functions are also simple functions. And in fact, that is the next point I'm going to make. But so you can see that and the integrals are the same. On Riemann integrable functions, they agree. Okay, so this I will leave to you. It is actually not, maybe I can put it into some homework and so on, which reminds me, I have to give you a homework. Okay, so here, functions which are not, which violate this, maybe, which are discontinuous everywhere, perhaps. So for example, the function which is 0 on rationals, 1 on irrationals, it is discontinuous everywhere, right? So it's easy to produce functions which violate this condition. But to produce a function which is not measurable, we have gone through that and it is not so easy. We have produced, but it is a not trivial thing. So that also indicates that all functions we might want to integrate are already fine. They are integrable, okay, in the Lebesgue sense. So that is one remark here. Any questions about this? I didn't say any concrete theorem here. This is just I recalled the comparison to Riemann integral, which is something that you should definitely know to appreciate. Not for logically, you don't need to know, but to really appreciate what has been done, you should realize this. So, but how did this happen? It looked very much like the Riemann integral definition only, right? As somebody pointed out the other day when I was doing this. Well, what did we do for I2? I3 was nothing. I3 was just separating f into two parts and then defining blah, blah. But the key part was, okay, simple functions, of course, is fine. So the I2 part, it was like, yeah, you were approximating by simple functions and doing. So how is this different from Riemann integral? Riemann integral, you used to use step functions and approximate, right? You sandwich between step functions, and then if for step functions, you know what integrals should be. And if you can sandwich between sequence of step functions so that from inside and outside you get the same answer, then that's what you define as a Riemann integrable function. Right? So how did Lebesgue integral turn out to be powerful? It looks pretty much the same. So the subtle point, the really clever, so to speak, thing in Lebesgue integral, again, to make a comparison, let's stick to, again, let us again just for simplicity, 0, 1. Okay. So we have some function here. So we have a function. So let's take some function. So I have drawn a nice enough looking function. So on 0, 1. In Riemann integration, what we do is we sandwich in between step functions, right? Okay, enough. Or from outside. Okay, so in Riemann integral, you approximate by so you are really dividing. So what you do is this is small. You divide x-axis into tiny intervals. Okay, that reminds me, I left out something, but I am now fully convinced people are sleeping. I left out something in the proof and nobody objected. So I'll go come back to that after this. So what is Lebesgue's idea? Lebesgue's idea is actually, the real difference between Riemann and Lebesgue is the difference between step functions and simple functions. Step functions are simple functions, but not the converse. So what Lebesgue is actually doing is dividing in the y-axis. Okay, so really what Lebesgue is doing is dividing in the y-axis. Okay, and what we do is, okay, so this function doesn't look good enough, so let me just draw a different function. So suppose my function looks like this. Okay, so what Lebesgue is doing is approximate. How do you approximate it with simple functions? Okay, so you divide the y-axis into small intervals. Okay, so and you look at the set of the subset of x for which it belongs to one of these intervals. Okay, so let's say I have marked one particular interval. No, maybe I mark a different interval. Sorry. So let me take an interval like this. Let me take this interval. Let me take this interval. Okay. So you take the value here. Okay, so let the lower end be y. So here what we are doing is, if this is x and this is, so you are approximating this area by, this is you are saying is approximately this width is delta times the height of the function, which is f of x at this. Here, what is it we do? Y2 and this length is, let us say, delta. So you look at all those points where the function value lies between this. Okay, so that gives us actually multiple intervals. Actually, it gives you a rather complicated. In general, it's not even a union of intervals. It's a complicated measurable set. So, for example, here we get a tiny piece here till it gets out of that interval. Then we get it. So it has to lie between this. So this part is here. So we get one interval here. Between this and this, we get one interval here, slightly longer. And then we get another interval here. Okay. So what we do is, so this is this set, let us call it a y comma delta. These are the points where the value is in y to y plus delta. And what we do is we approximate the contribution of this part by delta times, sorry, not delta, y times, y is the value there, y times the Lebesgue measure of a y delta. Okay, or in other words, if you are confused, what the hell am I saying? To approximate this function by a simple function, what we do is we take the set where it is between y and y plus delta, and you take a simple function which takes the value y on this entire interval and do it for all such intervals. Okay, and where it is between this and this, you take the lower value. So then you get a simple function. You get y on this set, you get a different y on a different set, and so on. So that gives you a simple function, and the contribution coming from this set will be y times the measure of this. So the intelligent thing that Lebesgue did as compared to Riemann is he divided on the y-axis instead of on the x-axis. So that viewpoint, change of viewpoint, actually gave this amazingly more powerful integral. Okay, so that's what happens. So maybe this point is not entirely clear. Actually, I skipped one step, so it will be. Is there any question here, by the way? So this is where the power of Lebesgue integral comes. The division is on the y-axis. This point is not entirely clear because I actually skipped a step in the proof and nobody pointed, which is why I'm now convinced you are sleeping. Okay, which is okay, I don't mind. But what is the part? I said, suppose in this part where the key part where we were showing additivity of I2, I said, suppose we can find simple functions which increase to f and simple functions which increase to g. I had to prove this, no? How do you know there exists such a thing? So do you remember? Okay, I will not ask embarrassing questions. So let's say this proof actually used the fact that if f is, so here is the fact that I have to prove really. Let's write in green here. So what is a fact that we have to prove is that if f is non-negative and measurable, then there exists simple non-negative measurable functions phi n such that phi n's increase to f pointwise. If phi n's increase to x pointwise, this is the fact, which is what implies this. But how do I prove that? Actually, that is what sort of I was explaining a moment ago by dividing on the y-axis. So I will explain to you now. Now you put this and that together, you will understand. So the proof is like this. So let me write that picture I had written before again. So I have a function like this. So I am writing a function on the real axis, real line, but it's the same idea. So what we do is you divide the y-axis into tiny pieces. And you look at the set of x for which it takes values between in this interval.
It's 5 o'clock.
And on that, for all those points, you set the lower value, let us say, for example. So that's what. Let me write down explicitly in phi n and then explain what that is. So I can write down explicitly phi n. Phi n is like this. It is okay. So rather than write it with this, so let's just write it as cases. Phi n of x I will define it to be k over 2 to the power n. Okay, so my delta here, I am taking it to be 1 over 2 to the n. Okay, so that is my spacing in the y, how I divide in the y-axis. So it will be k over 2 to the n if fx is between k over 2 to the n. So here I have put a, let me be a bit more legible here. If okay, for what k? For up to what shall I take? See, so I take here. So in other words, if it is between 0 and 1 over 2 to the n, any point where fx takes the values between 0 and 1 over 2 to the n, I set phi n of x to be 0. And when fx is between 1 over 2 to the n and 2 over 2 to the n, I set it to be 1 over 2 to the n, and so on. I keep doing like this till how long will I go? Well, I can go up to 2 to the n, but what I will do is I also want to cover the entire y-axis range, but for any n, I have to go only a finite distance. So what we will do is let's do 2 to the n times n minus 1. And then this covers everything up to fx less than n, because when k is 2 to the n, when k is this, what is this k plus 1 is 2 to the n divided by 2 to the n will be n. So fx less than n is covered. So if fx is greater than equal to n, then I will just set it to be equal to n. Okay, so these phi n's are simple functions. Okay, so because they take finitely many values, so these are the functions. So check phi n's increase to f. These are simple and measurable and all that. Okay, so let's just say in words. It is simple is clear, right? It takes only finitely many values, 0 over 2 to the n, 1 over 2 to the n, up to n over 2 to the n, and n. I mean, that is sorry, up to n. Yeah, so it's finitely many values. That is clear. So it is simple. Why is it measurable? Well, it is another way to write this if you want. If you want to write it the indicator, so I can write phi n as summation k over 2 to the n, indicator 0 less than equal to f, sorry, k over 2 to the n less than equal to f less than k plus 1 over 2 to the n. Sum of k equals 0 to n times 2 to the n minus 1 plus n times indicator f greater than equal to n. So you have written it as a sum of indicators, and you see that this is actually all these sets are measurable because f is measurable. These sets f between two values or f greater than equal to n, they are measurable sets. So phi n is measurable. So simple measurable. But why do phi n's increase? Okay, phi n's get close to f is kind of clear because we are making the mesh size smaller and smaller. So it becomes closer and closer to f. That is sort of clear. But why did we choose dyadics? Why did we do 2 to the n? Because then these partitions become refinements. When you do it with n, you get this partition. When you do it with n plus 1, you just divide each interval further into half. It's not like if I divide first into 0, half, 2 times half, and so on. And next time I do into 0, 1/3, 2/3, and so on. Then these refinements, this is not a refinement of the other one. They don't match, right? Whereas if I use dyadics 2, 4, 8, and so on, then what I do is I refine the partition further and further. So that's why this is actually better. Okay, so I will leave this as exercise. Once you do that, this part is also becomes clear. What I am saying here is becomes more clear. Okay, sorry, I realize now I'm already over time. I'll stop here. We'll continue next time. Okay, any questions? Okay, already anyway, many people have left. Sorry about that. Okay, so that's all. So I will stop recording and